Okay, dynamic entry, setting up my microphone there. I think we're recording, I hope so. Okay, so let's get to some physics. So last time we were talking about capacitors and inductors, and capacitors are things that store charge. Remember we had capacitors, we had capacitors stored charge from Q is CV, or we had similarly, we took the derivative of this, we had I equals C dV by dt. So as a device whose current through it depends on the rate of change of the voltage. And we found that these things stored energy in the electric field actually. We also had inductors. Inductors had a similar equation, had a voltage given by the rate of change of the current, di by dt, for inductors, and that stored energy in the magnetic field. So today we're going to take this a step further and really go through, in my opinion, an exciting step in your electronics career. We're going to take this old Ohm's law equation. Here's Ohm's law, right? V is equal to I R. And we're going to make a huge advance. We're going to generalize Ohm's law. We're going to replace R with a Z. V is equal to I Z, where Z is called the impedance. Now this Z, maybe it's a resistor, maybe it could be a resistor, it could be a capacitor, or it could be an inductor. And all of the stuff we've done with Kirchhoff's laws and Thevenin equivalence, that still applies, except we just now have this more general Z, which is a impedance, not just a resistance. So let's get to that. So that is the way we look at electronics when it's driven with sine waves. Remember from the sine wave video, we had that the most important signal in physics is a sine wave because we can build up other signals from it using Fourier. So let's look at this concept of driving a capacitor with a sine wave and see what we get. So imagine we had a capacitor here, capacitance C, and somehow we have a sinusoidal voltage driven across it. Remember, in this course we're going to call a sine wave, maybe we're going to call it V0 sine omega t, maybe even some phase to it, or we might call it V0 e to the j omega t. And that's what we're going to use first of all. We'll do both actually today. We'll do both just so we're all comfortable with it. But we're going to drive it with a sine wave V0 e to the j omega t. And we're going to ask, what is the current? Okay, so we have this voltage, which is going positive, the negative, positive, and negative. Somehow we're going to have a current, which is going back and forth in a sinusoidal way. But what is that current? What is the magnitude of that current? So let's look at that. So I is equal to what? That is our question. So let's find the answer. We have the current is equal to C dV by dt. This is our fundamental equation for a capacitor. And we have, let's just write it a bit more legibly here. We have that our voltage, V of t, is V0 e to the j omega t. Now you see why we don't use I for imaginary number, we use j because that would be very confusing already. And it would get even more confusing in a few steps. So we can take the derivative of this function quite easily. Let's do that. So we have C times V0 d by dt of, well, let's just pull that in there. Let's not be too lazy. Let's just be lazy enough. C has the derivative of V0 e to the j omega t. Turns out this is a fairly simple derivative to deal with. So we take the derivative of this, we're just going to get the derivative of e to the ax is a times e to the x. So we're going to get a j omega out front. So we get j omega c times V0 e to the j omega t. Aha, but look at this. This is our original voltage that we had to start with. So it's equal to j omega c times v of t. That's what the current is. Now, let's write this in a v equals IR kind of way. So we're going to write equivalently V of t is equal to I of t times some stuff. Well, let's figure out what that stuff is when we look at this proportionality that we just figured out. We had I is equal to something times V, so we divide by that something. So we're going to go 1 over j omega c, and we're going to use a very sophisticated trick. 1 over j is equal to negative j. You can multiply the top and bottom by negative j to see that. So we're going to get times negative j over omega c. So we have V equals I times something. We're going to call this the impedance of the capacitor. And then we have V equals I Z. The voltage across the capacitor is equal to the current times this complex impedance. Okay? So we've derived the impedance. We see that when we drive a capacitor sinusoidally, the current is also a sinusoid, but it has a proportionality, which is a complex number. So let's pick this apart. First of all, let's note a few things. It has a phase. The elephant in the room is that it's imaginary. What does that actually mean? Well, we can use this funny looking identity here that negative j, that's actually the same thing as e to the minus j pi over 2. Okay, from our complex number review, we can write that using Euler's formula or however we want, or the Argand plane. We can see that it's directly going to be pointing at j. But either way, this j is just e to the j minus e to the minus j pi over 2, or 90 degrees. Okay, so we plug that back in, and what do we find is that my current is my voltage is proportional to current, but there's a 90 degree phase shift, right? Because if I have e to the omega t, e to the j omega t, which is my sine wave, times e to the minus j pi over 2, I can just factor that all together. That's e to the j omega t plus, or minus rather, pi over 2. Let's just be sassy and write it as 90 degrees, which is the same as pi over 2. Okay, so that is telling us that j, all it tells us is that we're shifted back and forth in time. Now, I said we'd do this with sines and cosines. Let's do the exact same thing very quickly with sines and see if we get the same thing. But this is a key point here. Okay, so V naught. Let's say we have V is equal to V naught times sine of omega t, and we know that our current is C times d by dt of our V naught sine omega t. Okay, derivative of sine, not too bad. It's omega times a cos, so this is omega c times V naught cosine of omega t. So we have a similar form. What I like the complex version, by the way, is that you can factor out the original voltage. Here we have to do a bit of work. We see the current, if the input is a sine wave, the current is a cos wave. And there's a trig identity we can apply here. That's a cos is just a sine that's shifted by 90 degrees plus pi over 2, or 90 degrees, however you want to say it. So we see that we get the original thing back. We pull in a sine wave. The current is a cosine wave, which is shifted by 90 degrees. Notice how we had a negative 90 degrees here. Well, here I'm saying the current is leading. It's advanced by 90 degrees. The voltage from our V equals IZ was lagging by 90 degrees. Same thing. So that is one point here. This J here, I better unerase this. This J here tells us that it's phase shifted by 90 degrees, okay? And we have our complex impedance. Just again, our impedance is minus j over omega c, all right? This is why the complex form is very nice. By using this complex form, we can write our V equals I Z, and we see immediately that we get a 90 degree phase shift and also a frequency dependent response. So the higher the frequency, the lower effective resistance. and the more current is going to flow. By the way, we don't actually call it resistance. We call it in general impedance, but there's an analogy to resistance, a frequency-dependent quantity, which is called the reactance. Okay? So let's keep this in our pocket for a sec and talk more generally now about reactance. So we have impedance. Let's put this in very important thing. Z. Z is the impedance, and it's in general a complex number. If the impedance is purely imaginary, right? So if it's J times 12, that's purely imaginary. If it's 12, then it's purely real. And if it's like 3 plus J times 4, then we say it's complex. It's a mix of real and imaginary parts. So if it's purely imaginary, we say that it is reactive. If it's purely real, then it's resistive. It's resistive in that case. Okay? So what is the big deal? It's really an interesting distinction here between reactive and resistive components. We'll get to that in one sec. But in this case, in the reactive case, whenever you have that J there, that means that it's plus or minus 90 degrees out of phase. The current is plus or minus 90 degrees out of phase with the voltage. If it's resistive, it's just a number. I is equal to 12 volts divided by 1 kilo ohm or something like that. So it's in phase and out of phase here. Why is that such a big deal? If the current is in phase with the voltage, remember we had this formula for the power. Power is equal to I times V. P is equal to IV we had. Now it's a bit weird when the current and voltages are now changing with time. So we have what's called the instantaneous power, which is like the power over a very short interval. But what we're often talking about is the average power when you have AC circuits, which is given by basically just integrating or averaging the power over a full cycle. So it's the integral of I of t times V of t dt. Okay? And this is where the distinction between reactive and resistive components comes in, right? Because let's look at the case. If we have a voltage like that and a current which is in phase, even if it's bigger or smaller, they're both positive at the same time, they're zero at the same time, and negative at the same time. We're effectively always going to get a positive number in this sum here. However, if we're lagging, or let's just say we're leading by 90 degrees, when one is there's cases where one is negative and the other one is positive, and vice versa, and they're not zero at the same time, despite my bad artistry making it almost look like they are, that we're going to have sometimes the power is going to be positive, we're dumping energy into the system, and sometimes it's going to be negative, we're extracting energy from the system. So let's see what that means. What does that actually mean for us? Well, for a resistive load, let's use sines and cosines, that if V is equal to V naught sine omega t, my current was equal to, in this case it was, would just be V, well, I is equal to V over R. So it's going to be V naught over R times sine of omega t. And let's look at our power. How much power are we, the average power that our circuit is dissipating? Well, it's going to be, if we factor all this stuff out, V squared over R. We average over a period. We'll get sines times 2, so 2 sines rather. Sine squared omega t dt. But this whole quantity here, in fact, this whole quantity here, this quantity here is a half. And this whole quantity is the RMS voltage. So this is equal to V naught squared over 2 over R, that's the power, or, let's just really belabor the point, V naught over root 2 all squared over R. Why am I writing it this way? This is my RMS. So this is equal to V RMS squared over R. The RMS tells us the equivalent voltage, the equivalent DC voltage that we'd get that would dissipate the same amount of power. So V squared over R. That's how much power we got for a resistive load. Let's look for a capacitive load. Let's look for a reactive load. We'll just do the same math. So now we have V of t is equal to V naught sine omega t, and we had that I of t, in this case, is equal to, there's no j because we're using sines and cosines, so we get omega, so I is equal to omega c cosine of omega t, and we're just going to perform this integral now. So we get V naught, times V naught, sorry, V naught squared omega c times the integral 1 over tau, or 1 over t, sorry, of sine omega t times cosine omega t dt. This actually turns out to be 0. So to see that, notice that there's a trig identity that says that this is equal to a half of sine 2 omega t. So this is equal to V naught squared omega c over 2 times, we integrate over a period, sine of 2 omega t dt. Easy enough integral to calculate. We're going to get minus V naught squared c over 4 t times cosine of 2 omega t evaluated at t and 0. So at 0, cos of 0 is 1, but at t it's also 1, right? Because this t, omega is 2 pi over t, so this is going to be cosine of 4 pi minus cosine of 0, and that's equal to 0. So the power dissipated by this capacitor is 0. It doesn't dissipate power, which is very interesting. So why not? Where does that power go? Well, in the case of the resistor, effectively the currents that were driving through it were banging around the atomic lattice, and the energy was being converted to heat and dissipating throughout the system. In the case of a capacitor, that energy is not going into the lattice vibrations. In fact, it is not a resistive load. Our archetypical capacitor was 2 parallel plates with no resistance. And what we're doing actually is we're building up an electric field. So the energy is getting dumped into an electric field in that region. And then when it reverses, when the slope goes to 0, the current goes to 0, there's no more current flowing, that field collapses, helping drive current the other way, and back and forth and back and forth. So the field is getting borrowed, or rather the energy is getting borrowed and put into the field, and then back into the current, back into the field, like that. So that is where the energy is going for a capacitor. And that's the big deal about reactive, misnomer for reactive circuits. Okay, so reactive circuits dissipate no power. They have a lag or lead by 90 degrees. Let's do one last thing. We had one more reactive circuit we talked about last time. We had our inductor. Let's do the exact same thing we did. My C's almost look like L's anyways, so almost didn't have to erase that. We had our inductor L there, okay? And we had our equation for an inductor. We had V of t is equal to V naught e to the j omega t, and that was equal to L di by dt. And we want to figure out I. Well, we don't take the derivative this time. What we can do is we can integrate both sides. So I'll just integrate both sides, and I'll say that L times the integral of di by dt over t is just going to be, the integral of a derivative is the function evaluated its endpoints. Let's just say it's originally 0. Okay, so that's going to be equal to V naught times the integral of e to the j omega t. I love complex exponentials. Very easy to take the integral and the derivative of, right? That's just going to bring down a j omega. So we're going to get V naught over j omega e to the j omega t, and that's equal to V of t, the original voltage, divided by j omega. And that's equal to, on the other side, L times I of t. Let's do the same old business as before. We'll get into a V equals IR form. So we have V of t is equal to I of t times j omega L. And that's our inductive reactance, or rather our inductive impedance is j omega L. Again, there's a phase shift there. There's a phase shift of 90 degrees. It's now positive instead of negative. And conversely, with higher frequencies, we get more impedance. The magnitude of this gets higher and higher. We're going to get less current flowing. For very low frequencies, basically there's no inductance. It just behaves like a wire. And it's going to basically dissipate drop no voltage. So let's just summarize what we've learned so far. So we had a resistor, capacitor, and an inductor. So our resistor, capacitor, and our inductor had, we'll call it a symbol. I guess that's the thing. The symbol is like that. The impedance was R for resistor. It was real. For capacitor is minus J over omega C. And inductor was J omega L. So the type of impedance it was resistive, reactive, and reactive. Finally, so the energy for the resistor went to heat. For the capacitor, it went to the electric field. How about the inductor? Well, so the capacitor was made of parallel plates, which is, the standard textbook way to make an electric field. The inductor is made of a coil of wire, which is the standard way to make a magnetic field. The energy goes into and out of the magnetic field. And the magnitude of the impedance was constant. For the capacitor, it decreases with frequency. And it increases for the inductor. So in fact, for very high frequencies, we can approximate a resistor by a resistor. We can approximate a capacitor with a wire. An inductor will look like an open circuit rather. And for very low frequencies near DC, well, our resistor is still a resistor. This capacitor is like an open circuit, and the inductor is like a short circuit. So we'll use that a few times in the coming lectures. Okay, so that is capacitive, so that is reactance. Let's do a couple more things. So first of all, let's do an example on paper or on whiteboard of what this actually looks like. So let's say we have the following circuit. We have a 1 microfarad capacitor, and across it we place 1 kilohertz of frequency. So our circuit looks like this. C. And in general, we're just going to draw this circuit in the future as some source in some Z. It might be a resistor, might be a capacitor, might be an inductor, or a combination of those things. And what is my current? How much current is going to flow in the system? Well, I is equal to V over Z. And in this case, I have V naught. Let's just say it's a 2 volt amplitude. So 4 volts peak to peak sine wave. So it's going to be 2 volts times e to the j omega. We'll just leave it as omega. It's 1 kilohertz. Let's just write that. 2 pi times 1 kilohertz times time divided by Z, which is negative j over omega c. So this is going to give me 2 times 2 pi times 10 to the 3 hertz times my capacitor, which is 10 to the minus 6 farads. That's omega c, times e to the, let's just write it as omega t times j. So we have a j up here, which is e to the j omega, which is e to the j pi over 2, right? We've got a j up there. So this is equal to 4 pi times 10 to the minus 3. This is amps times e to the j omega t plus 90 degrees. So my current is going to be 90 degrees ahead, and it's going to have a magnitude of 4 pi amps. What's 4 pi? It's going to be 12.5, 12.6-ish. I should probably know 4 pi, but let's just say it's around 12.6 milliamps times a cosine wave, if this is a sine wave, or a sine wave if it's a cosine, times my out of phase current by 90 degrees. And that's how we that's how we can attack this. There's a kind of a moniker. So sometimes you call voltages EMFs. We don't do it too much in this course, but there's a moniker to remind us is that I remember learning. Eli, the Iceman. I don't know who comes up with this, but so E is like EMF or voltage. So voltage leads current in an inductor. In an inductor, voltage leads the current, and current leads the voltage in a capacitor. Eli the Iceman. All right. So that's how it works. But let's actually test this out. This lagging and leading is kind of an interesting and weird thing. So let's find out how we'd actually measure it. Let's go over to the workbench and construct a few circuits and see if we can measure it. Okay, so let's test this experimentally. Let's look at the current through a capacitor or an inductor as a function of the voltage through it. And let's look at the phase relation between these quantities. So we'll start with an inductor here. Now the problem is, to measure the current, we need to use a trick. I have an oscilloscope, but it does not measure current. But what we're going to do is we'll have our circuit. That's going to give me my AC voltage, my sine wave. And I'm going to put a resistor here, and that resistor, its sole job is going to be to measure the voltage drop across it, and therefore the current through this series circuit. So we'll start off with my inductor here, eventually move to a capacitor, and we can measure delta V across the inductor. We can also measure delta V across the resistor, and that's equal to IR. So whatever the voltage drop is across this resistor is going to be proportional to the current through this whole thing, including the inductor. So let's plug it in and have a look on the oscilloscope. And what I'm going to do is, the oscilloscope it can only have one ground, so I'm going to call this whole thing ground. I'll measure the total voltage. Let's actually just have a look. We have the total voltage in yellow, and in blue we have the voltage across the inductor, and in red I've just subtracted the two. So red is equal to V total minus V of the inductor, And from Kirchhoff's laws, we have V resistor plus V inductor is equal to V total. So V total minus VL is going to give me the voltage across a resistor, and that's directly proportional to the current. Okay, a lot of setup. Let's see what we actually get in this case. So it looks like we have, let's actually have a better look at this here. If we zoom out, we have our yellow trace, which is the total voltage, and this particular frequency, which is, according to the measurement, about 2.5 kilohertz. At that particular frequency, it looks like I'm dropping about as much voltage across my resistor as my capacitor. So that's what we have here. But notice that there's a time difference between the red trace, the current, and in the inductor. In fact, the inductor is happening at an earlier time. It's leading the current through the system here, which is quite interesting. And we can calculate the phase. We have these cursor measurements here. So I'll hit cursor, and we can see that cursor 1 is, oops, that's the offset, wrong button. Cursor 1 is at about 270 when that zero crossing happens, when the blue one crosses 0. Cursor 2 will be when the red one crosses 0, and that's at negative 170. So negative 270 minus negative 170. There's a 100 microsecond phase shift or time delay from that. Now what does that actually mean experimentally? We can measure that, remember. Let's have a look at that. So remember that my phase, by definition, delta phi, was equal to, or rather the phase over 2 pi, here's a nice way to remember it, was equal to the time, the delta t, over a full period. Delta phi, my phase shift, is equal to 2 pi times 1 over t, which is f, times delta t. In this case, I have 2 pi times 2500 hertz, 2500 hertz, and delta t is 100 microseconds, or 10 to the minus 4 seconds. So I have 2500 times 10 to the minus 4, that's 0.25, times 2 gives me pi times a half, or pi over 2. So my phase shift is indeed pi over 2 radians. Eli. Okay, so let's look at our the other case here, our capacitor. So we'll pull this out, and we'll put in our 470 microfarad capacitor in its place, and we'll measure the current in the same way. What do we have now on the oscilloscope? Well, for this particular frequency, it looks like the current is nearly 0. I wonder why that is. Maybe we've chosen too low of a frequency. Let's crank it up a bit. I'm just going to increase my frequency knob here, and we'll see why this is the case in a later lecture. I'm going to make it faster, and I'm going to have to make it much faster. Get some nice aliasing there, or aliening. We'll learn about that too in due time. There we go. So this is about the right time scale. So let's look at the current there. They're about equal now. It's just going to make our cursors a bit easier to measure. So we have a frequency, according to my oscilloscope, of about 276 kilohertz. And if I can move my cursors here, let's find some zero crossings. Notice that now the current is on the other side. The current leads the voltage because of Eli. Okay, so let's see, our delta t here, if we're zeroing in, is about 820 nanoseconds. And we can do that math too. So we can look at that phase and verify that 820 nanoseconds over, what was it, 276 kilohertz, should roughly be 90 degrees. Let's go ahead and do that. Let's work that out. So we have now, what was our formula again? 2 pi times 276 kilohertz times 820 nanoseconds times 10 to the minus 9 seconds equals, well, let's just say that it's going to be equal to pi times 2 times 2.76 times 10 to the 5 times 8.2 times 10 to the minus 7. And that's going to be equal to, well, this 10 to the minus 5, 10 to the minus 7 gives me 10 to the minus 2, which is 2 times 2 point, is this going to work? 2 times 2.76 times 8.2. You know what, guys? Calculator time. Which is 45 times 10 to the minus 2, or about 0.5. So pi times 0.45. And we've rounded down a few things. It was 2.76 something. That last significant figure here. This is pretty much our 90 degrees. But now it's a 90 degree phase shift where the current is leading the voltage, or the EMF, in this Eli, the Iceman nomenclature. Anyway, let's look at the scaling of the current as a function of frequency. Now the current should decrease for a capacitor, the resistance, or the impedance rather, should decrease with increasing frequency, so we should get more current. And let's crank it up a bit. We're pushing the limits of this breadboard, but let's do it. Indeed we do get more current. Let's crank it down now the other way. And we're going to have to scale out on our oscilloscope here. Where's that red trace? And we're going to crank down the frequency, and indeed we get a smaller and smaller current for lower frequency because the impedance is increasing. More effective resistance, frequency-dependent resistance, means less current. If we do a quick swap, we should get the opposite behavior. So as I crank up the frequency, the current, the resistance goes down, and it'll make it very slow, and the current gets big because we have a very low impedance. All right, it looks like it all makes sense.